Hello. Today I would like to talk about solutions to black hole equations, and in particular to describe where the singularity comes from and also why we say that time seems to stop at the horizon and where that arises in terms of the mathematical equations. First, let's just think about what we mean by a metric, which comes from general relativity. So we can imagine there's some observer who's measuring some event in the universe with a coordinate frame. So this is their space and this is their time. We're using a one space dimension here. Obviously in our space dimensions there's x, y and z, three spatial dimensions, one of time, but it's very difficult to plot that. And there's some event which is observed. Okay, it may be, for example, a supernova explosion. And so you can measure it in this coordinate frame, where it is in space and where it is in time, or when it is in time. But there's another observer over here who's also got their own coordinate frame, and it's different. It's different positions. So their space might be here and their time is here, and they're also measuring this event in some way. So the line would extend to here, of course. So this is observer 1 and this is observer 2. And the interesting thing that comes out of relativity is that they would disagree on the measurement. They wouldn't necessarily agree where in time and space it was. And so instead we use something in relativity called a metric, which is defined by an interval, which we call the space-time interval. And if I write that as squared, is equal to the separation in time, let's just do delta t squared, minus separation in space, delta s squared. And actually we could write this as ds squared, dt squared minus delta s squared. So this is kind of an interval of time, space, and we call this the space-time interval. And why this is interesting is that although the two observers may disagree on the measurement of these two quantities, they will both agree on the space-time interval. So that's the power of a metric and why it's so useful in relativity. The invariance of the space-time interval forces us to recognize that time cannot be separated from space. That's why we use the phrase space-time. Space and time are in fact a part of a single entity, space-time. Space has three dimensions of length, width and height, and time has one dimension, which goes forward. And the interval combines all four dimensions in a single expression, and that's what this space-time interval is. And so the geometry of space-time can be thought of as four-dimensional. And the numerical value of this interval is the same for all observers, no matter how fast they are moving relative to one another. And we can kind of rewrite this space-time interval in a slightly different way. Just call it s squared is equal to minus c squared tau squared plus x squared plus y squared plus z squared, where these have the dimensions of length, and so does this, because c is the speed of light and this is time. So c is obviously meters per second times by time, which is in seconds, so they cancel. So this is also in the length units of meters, except it's squared. Whole thing is squared. And so this is a kind of length duration measured for the time dimension, and this is the length dimensions of the three coordinates, and this is the space-time interval. So contrary to Newtonian mechanics, two observers measuring the distance and time intervals of an event from separate locations will not agree on their measurements, but thanks to special relativity, they will both agree on the metric. They will agree on the space-time interval. And this tau term, which we wrote here, is actually referred to as the proper time, and S is the proper distance. The proper time and proper distance between events or coordinates are invariant for all observers and can be written as a line element or metric. So this is referred to as a metric. Let us write this equation again in the language of relativity. So how we actually write it, the metric as ds squared is equal to minus c squared dt squared plus dx squared plus dy squared plus dz squared. And notice that the x, y and z's all have a positive operation and the time term has a negative. And you can actually write them either way, but the time is always opposite to the space terms. This is the space-time interval, the space-time metric. And actually this is specified for flat Minkowskian space-time. Minkowski, who was a famous physicist, mathematician. And another way to think about this is actually written in Cartesian coordinates because it's x, y and z, but we could also write it in polar coordinates. So that would be ds squared is equal to minus dt squared plus dr squared plus r squared d theta squared plus the sine squared theta d phi squared. So this is a polar coordinate form. We've got some coordinate system and some radius r in that coordinate system. So this would be your theta, and your phi term would be relative to this. And so this is a polar coordinate form way of visualizing the Cartesian metric. And both those just describe the space-time interval as equal to minus the time interval plus the space interval. Now the key thing to know about both of these forms is that they are describing flat Minkowski space, which means there's no gravitational fields. There's no mass, because mass is what gives rise to gravity. So what if you had a spherically symmetric object in space, like a star or a planet, which had gravity? What would the metric look like? Well, let's write down the equation, which was first derived by Carl Schwarzschild after he became familiar with Einstein's general relativity theory. So again, it's ds squared, the space-time interval, is equal to minus, now this is going to be our time coordinate term, 1 minus rg, explain what rg is in a minute, over r dt squared plus 1 minus rg divided by r to the power of minus 1, which means 1 over dr squared, and then you have the other terms, which we're going to ignore in a moment, but let's just write those down here. D theta squared plus sine squared theta d phi squared. What I want to do is to focus on these two terms here and see what happens as r approaches rg. But first, let's just remind ourselves what rg means. Rg is the gravitational radius also known as the Schwarzschild radius, which is 2gm over c squared, where m is the mass of your object and g is the gravitational constant, 6.67 times 10 to the minus 11 meter cube per kilogram per second squared. And so, if for example you wanted to work out for an object how small you'd have to shrink it in order for it to collapse within its horizon, its event horizon, in other words become a black hole, you simply calculate it from this equation. So the mass of the Sun is 2 times by 10 to the power of 30 kilograms. G, I mentioned, is 6.67 times 10 to the minus 11 in the units that I referred to, which is meter cubed per kilogram second squared. And then C is the vacuum speed of light, which is just right here is 3 times 10 to the 8 meters per second. And if you were to calculate this for the Sun, you would get a gravitational radius approximately equal to 3 kilometers. And if you were to do it to the Earth has a mass of 5.9 times by 10 to the 24 kilograms. So it's a million times smaller than the Sun in mass. You get a gravitational radius of something like 2 centimeters in order for it to get to a point where light can't escape, because the escape velocity is so large not even light can escape. That is the essence of what we mean by a black hole, because light cannot escape from it due to its escape velocity being so high, exceeding even the speed of light. Now it's important to note that this equation, known as the Schwarzschild metric, written in polar coordinate form, describes the events on a plane that passes through the center of a spherically symmetric, non-spinning center of gravitational attraction. It's a gravitational mass. So we assume it's not spinning and it has no electric fields, magnetic fields. It's just a piece of mass that's spherically symmetric sitting there, which is one of the simplest kind of black holes you can analyze. What we want to understand is what happens as R approaches RG. So we can imagine we have some object like a planet or a star, spherically symmetric object, and it's got some gravitational radius coming off its center, and perhaps you're over here as an observer and you're watching as some giant spacecraft, funny looking spacecraft, is going to head in towards this, down this R coordinate, until it gets to a point equal to RG. And so we want to understand what happens to dr squared and what happens to dt squared. And so for this analysis, we are going to pretty much ignore all of this, and we're just going to focus on these two terms, just trying to keep things simple. So we'll write out the first term, which is here. So we've got minus 1 minus Rg over R dt squared. Well, we can see that as R approaches Rg, eventually R equals Rg. When they're equal to each other, this whole term becomes 1. Unity. Which means now you've got minus 1 minus 1 dt squared. 1 minus 1 is 0. So this whole term tends to 0, which is very interesting. And essentially what that means is, because 0 times by any term, which is dt squared, is 0, that means that time tends to 0 at the event horizon when r is equal to rg. So from the perspective of the observer, they see a spacecraft getting slower and slower until it eventually gets to that horizon and it appears to stop. It doesn't actually stop, but that's the perspective of the observer who's outside the horizon watching on. What about for the other term? Well, let's write that one out. So now we've got plus 1 minus rg over r, the power of minus 1 dr squared. Well, that's r goes to rg, once again we get 1. So that's 1 minus 1. So now you've got plus 1 minus 1 to the minus 1 dr squared, which can also be written as tending to 1 over 0 dr squared. Well, 1 over 0 tends towards infinity dr squared. And so what we can say from this is that the radius, the r term, tends to infinity. And essentially what's happening here, we've got some astrophysical object like a star that's collapsing towards its center, and its radius is becoming infinitesimally small. And so if its radius is becoming small, then its volume is also becoming small, and so its density goes up. It gets incredibly compressed. And so we see from this a simple implication that for a simple spherically symmetric object with mass, assuming no rotation or electric fields, which is a different problem, that the origin of the event horizon and how we visualize it comes out of thinking about the limits of these two terms up here. The dt squared term, where r goes to rg, and this whole term goes to 0, so time appears to stop from the perspective of an observer. And with this equation, rg over r again goes to 1, 1 minus that, but it's 1 over 1 minus that goes to infinity. And so the radius becomes infinitesimally small, but it's compressed up to high density. And so that's why we say any object that approaches the center gets crushed, because it's infinitesimally dense and the volume gets incredibly small as the thing gets crushed up. And so this is essentially how we define a black hole around the radius, the event horizon at rg, from the perspective of an observer who's watching on as the spacecraft approaches that rg coordinate. So the best thing to do is to avoid flying into a black hole. This is not the same as wormholes, that's a completely different subject, and it's not the same as a black hole that would be rotating or have electric fields. They have different solutions, and we will deal with those in a separate lecture. That's it.